Hello everyone, my name is Narjas Bozorg and today I'm going to talk about the paper Acoustic to Articulatory Inversion with Deep Autoregressive Articulatory WaveNet. Here we have the overview of this presentation. For the introduction, I'm going to talk about the acoustic to articulatory inversion. Well, the human speech is generated through the movement of a complex set of articulators, including the tongue, jaw, and lips, controlled together through the speech production process. Reversing the process to estimate articulatory movements from the speech signal, known as acoustic to articulatory inversion. Acoustic to articulatory inversion, or AAI, is the nonlinear regression problem of estimating articulatory trajectories from the acoustic signal. AAI is an ill-posed problem since it is highly nonlinear and different combinations of articulatory movements can be the source of similar generated speech signal. Well, the accurate approximation of articulatory movements and positions from the acoustic signals can be useful in several domains, such as audiovisual synthesis, computer-aided language learning, or CALL, and computer-aided pronunciation training, or CAPT. AI can also be used for improving the quality of speech synthesis and creating accurate kinematics for speech animation in video games or avatars. The articulatory WaveNet approach that has been proposed in this paper is evaluated using the corpus which is named EMA-MAE. This represents for electromagnetic articulographic corpus of Mandarin accented English speaker. EMA-MAE includes 40 total speakers, including both native L1 and second language L2 speakers balanced across gender. There are an L1 group of 10 males and 10 females native English speakers, and also L2 speakers, a group of 20 speakers. In the study is presented here, we only considered the L1 group of speakers. Articulatory data from the EMA-MAE were collected on a Northern Digital Incorporation wave speech research system with 5 degrees of freedom sensors at a 400 Hz sampling rate. To record the articulatory data sensors in the mid-sagittal plane collect information about the jaw, lower lip, upper lip, tongue body, and tongue tip. Moreover, 2 lateral direction sensors were also included, one at the right corner of the mouth and one at the right central midpoint of the tongue body. For each individual speaker, about 45 minutes of acoustic and articulatory data were collected, including word, sentences, and paragraph-level speech samples. The articulatory sensors are the reference sensors, which represents with REF, jaw sensor at the lower middle incisor, which we represented by MI, lower lip, upper lip, tongue dorsum, and tongue apex, or TA, all placed in the mid-sagittal plane, which represents in the left side picture. And there are also 2 lateral sensors, lateral lip sensor that is at the left corner of the mouth to help indicate the lip rounding, and the lateral tongue or LT sensor at the left central midpoint of the tongue body. Well, in this experiment, 10 articulatory features have been selected to model the kinematic space of the AAI process. There are 6 features to model the tongue movements, 3 lip-related features, and the feature to track the jaw movements. The table represents the vocal tract VT articulatory features that has been applied in evaluating the articulatory WaveNet system model. For acoustic data, male spectrogram features have been acquired to represent the acoustic information space. Male spectrograms are extracted through a Hanning-windowed short-time Fourier transform with 38.7 millisecond frame size and 9.7 millisecond frame hop size. Log dynamic range compression is implemented using an 80 channels of mil filter bank spanning the range of the 125 Hz to 7.6 kilohertz. In this paper, we introduced the Articulatory WaveNet, or AWN, which consists of the stacked dilated convolutional layer to model the conditional probability distribution and provides the accurate estimation of articulatory trajectories from the acoustic signals. This fully probabilistic autoregressive architecture predicts the articulatory trajectories from a given acoustic signals by utilizing the causal conditional predictive distribution of the samples. The core of this specific deep autoregressive architecture is the causal or masked convolutional layers. For causal convolutional operations, the occurrence of each sample X is conditioned on the previous samples. By this assumption, the dependencies on future events or samples are eliminated and all probabilities can be generated in one forward pass. Therefore, AWN models the time series articulatory trajectories with the shifted convolutional results for the required time steps. The property of dilated causal convolution not only captures the long-term dependencies between these samples, but also significantly grows the receptive field of the network. The goal of AWN is to model the sequence of articulatory trajectories that have been conditioned on the sequence of time series acoustic features. The predicted articulatory trajectories are synthesized from the fully trained network. The conditional probability distribution of articulatory samples xt is represented by the following equation, where in this equation, ht represents the conditioning Mel spectrogram features. The figure at this slide illustrates the AWN architecture. The AWN has been built up from the stacked convolutional layers. Each stack contains nonlinear activation units for modeling the nonlinear acoustic and articulatory time series signal. And it follows up by the residual and parameterized skip connection to speed up the convergence and enable us to design the deeper architecture. Well, the gate activation for the input X and output gate Z at the previous slide architecture is computed from the following equation. In this equation, the asteroid represents the convolutional operator. Circle dot is an element-wise multiplication operator. We here have the logistic sigmoid function. K is the layer index. F and G are the filter and gate indices respectively, and W and V are the convolutional filter weight matrices for articulatory and acoustic features respectively. Well, to adapt this sensor articulatory trajectory information with the range of -1 to 1 to be compatible with the activation function tangent hyperbolic, we scale the articulatory trajectories to this range using the global dynamic range normalizations. Well, for modeling the AAI, AWN deploys 24 layers with the 4 dilation stacks. At each layer in each stack, the dilation increases with the rate stepped geometrically by factor of 2, which results in 1, 2, 4, 8, 16, and 32 dilations for each stack. Causal dilated convolutions in AWN have a kernel size of 3, with 512 units in the gating layer, and the residual connection channels, and the 256 hidden units at the skip connection channel. And at the end, 1 by 1 convolution before the output layer. The AWN network was trained for 20,000 epochs and are 8 mini batches, with each mini batch containing a maximum of 8,000 time steps, which is roughly 302 milliseconds. The output is modeled as a mixture of 10 logistic components for higher quality. To compute the logistic mixture distribution, the AWN stack output is passed through a ReLU activation followed by a linear projection to predict the parameters, mean, log scale, and the mixture weights for each mixture component. In this experiment, we considered the loss as the negative log likelihood of the ground truth samples, which is obtained by this formula. Well, the performance of the AWN for acoustic to articulatory inversion has been evaluated across 20 native English speakers or L1 speakers for 10 articulatory features. This table reports the results of the RMSE and correlation coefficients scores across all the articulatory features for 2 different architectures: AWN, Articulatory WaveNet, and the HMM-GMM. The table also demonstrates the percentage of the improvement, which we represent by %, for these 2 different models. Our results from the AWN suggest that using stacked causal convolutional layers have significantly improved the AI performance compared to the previous GMM-HMM. HMM baseline method across all the L1 speakers from the EMA-MAE corpus. The average correlation for all articulatory features improved about 30%, and for the RMSE, the percentage of the improvement is around 59%. Correlation results show a consistent improvement across all the features, with all 10 of the articulatory feature trajectories having correlations around 80%. Well, this slide demonstrates some examples of the utterances for different speakers and different articulators to compare the estimated trajectories with the true measured EMA. At this slide, at the conclusion, we want to say that the proposed AWN model in this paper represents a novel approach for acoustic to articulatory inversion. The results on the EMA-MAE corpus shows a significant improvement compared to the baseline GMM-HMM framework, with an average correlation of 82%, and RMSE of 1.08 millimeter, demonstrating a similar correlation, and substantially improve the RMSE compared to the best current method of inversion. The future work will include the extending of the approach for a speaker-independent acoustic to articulatory inversion, and also we will have the comparisons between the different subgroup of speakers at the EMA-MAE corpus, which would be about the different genders and different dialect factors. Well, that was the presentation, and thank you for listening.